Okay, let's go through some simple calculations to show how this Tibetan plateau heating sets up the meridional circulation and what are the specific details needed to drive such a meridional circulation and why the Indian monsoon is different than West African and Australian monsoon in terms of how far north the precipitation goes during the Indian summer monsoon. This is just a simple radiative convective model calculation, which means you take a air column and you assume that the radiative heating is being balanced by convection in the atmosphere, and then you look for the lapse rates that satisfy this condition. So we start with an assumed radiative profile over the Ganges plain. So that is shown by this BCF, and the north of the Ganges plain, if you didn't have the heating etc., you would get a cooler boreal winter profile like ADE. But what is happening over the Tibetan plateau? So you assume that the temperature at the surface is similar to that over the Ganges plain, and then you look for solutions over the height above the Tibetan plateau, okay, where the plateau is located. So you are basically trying to see how different the profile is because of the heating and the latent heat release, and then what the consequences are. So the yellow region here contains all possible temperature profiles above the plateau depending on the assumed lapse rate above the plateau itself, the Himalayan Tibetan plateau. If the lapse rate is identical to the atmosphere above the Ganges plain for all but the unphysical assumptions, then the temperature difference between F and N at Z equal to Zn above the plateau and above the Ganges plain, the difference is positive, which means the profile above the plateau is warmer than over the Ganges plain. Okay, which basically means you have dt dy here. This is to the north of the Ganges plain, so you have created a positive gradient, and you know that when we have negative gradients to the away from the equator, we end up with vertical shear and westerly thermal winds, whereas if you reverse the gradient and create increasing meridional gradient, then you expect an easterly jet, which is consistent with the circulation we get over the monsoon region. So that's the first thing to heuristically argue based on the convective radiative model, that in a simple sense the latent heat release on the Tibetan plateau is going to give us a increasing increasing temperature gradient from the Ganges plain to the Tibetan plateau, and that's going to give us the easterly jet, which is consistent. And then north of the Tibetan plateau you again have decreasing temperature gradient, so you get into the mid latitude westerly. Oops, sorry, I don't know what happened there. Okay. So what else happens? Then you also need to explain the heating and expect that there will be a cyclonic circulation. If you look in the upper atmosphere or Tibet, you see an anticyclone. So is there a cyclone at the surface? We can start by looking at the precipitation. This is showing precipitation per month over the Himalayan Tibetan plateau, and you can see by March, April there is I've split this into two halves to be able to fit. So here is March, April, May, June, July, and so on. So as we said before, even during the warm season, as soon as the spring sets in, there is already precipitation here, which is not just rain, it has snow and hail and so on because of the lapse rates and the elevation, etc. But there is clearly surface precipitation, which means heat heating, and you expect convergence and cyclonic circulation. So that is also consistent with what we expect with the heating over the Himalayas in terms of setting up the stream functions, the relative vorticities. So you can clearly see that by April you're already creating cyclonic circulation, northern hemisphere. By May there is a very nicely set up cyclonic circulation that's clearly seen in stream function as well as so the circulation, as well as relative vorticity at 500 hectopascal mean surface of the Himalayan Tibetan plateau. Okay, so that is consistent with what we expect, and that's the percentage of annual precipitation falling by June, which is in the range of 30 to 35 at the highest to the south of the foothills and over the Tibetan plateau itself. So again, there's a consistency between the elevated heating, associated precipitation, and the convergent cyclonic circulation. This is then has to be related to how strong this heating has to be able to drive this meridional circulation. It turns out that as the heating is shifted away from the equator either into the southern or northern hemisphere, to set up direct thermal circulation of rising motion over the heating and then divergence and sinking elsewhere, you need the heating to be strong enough. There is a threshold that we will look at, and we also know that over time, millions of years, the Indian subcontinent has moved across the equator, crashed into the Asian landmass, and is still continuing to push northward, which created the Himalayan mountains. So as you can imagine, climate of the equatorial Indian Ocean and southern Asia changed at about 6 to 9 million years when the current configuration of the Himalayas got set up. Monsoon winds apparently strengthening, northern Pakistan becoming more arid to the west, but weathering of rock in the eastern Himalaya apparently increased, corresponding to the setting up of the monsoon and heavy precipitation, and all the freshly brought up material gets weathered, and there are sedimentary evidences which give you these timings that you can look at in terms of evolution of the monsoon and the evolution of the mountains and so on. So Peter Molnar has a series of articles on this nice geologic science of it. We looked at this before in terms of the circulations in the latitudinal height plane at 25 north, which is corresponding to the Tibetan heating, and you have the rising motion, divergence, and then these two zonal cells. So if you looked at the meridional section, we already talked about how around 30 north at the latitude of the Tibetan plateau, you have the strong heating, the precipitation that we just saw, the rising motion, and then you have this cell towards the north of the Tibetan plateau and to the south of the Tibetan plateau with this near equatorial cell. And as the heating gets stronger and stronger, the circulation gets set up, and then the equatorial cell itself may get modified depending on how strong this heating gets, but I won't get into that here. There are nice papers written on that. To look at the conditions required to set up this kind of meridional circulation that can be related to the heating, we can start by the momentum equation in a simple steady flow where we are just balancing the Coriolis term with the pressure gradient. Assume that the zonal averaged meridional circulation circulation is zonally symmetric so that the longitudinal gradient can be ignored, in which case we can use hydrostatic balance and equation of state to write the gradient of pressure in terms of the latitudinal gradient of temperature and write the vertical shear. Basically, this is our thermal wind relation, and all we have to do is then relate the temperature gradient to the heating rates. So what is the mechanism? Essentially here we are going to look for conservation of angular momentum, which is given by the distance from the axis of rotation a cosine phi at any latitude phi times the azimuthal velocity, zonal velocity. So omega a cosine phi plus u bar, which is the steady background basic state with the vertical shear, and this is the perturbation. Sorry, that's the acquired momentum. So if you move a parcel of air from the equator towards higher latitudes, it's going to keep acquiring angular momentum. And the solution we are looking for is that angular momentum is conserved, so dma dt is 0. Expanding that, dma dt plus v tilde dot grad ma equals 0. So for steady state we can drop this term, and then we see that the meridional circulation has to be normal to the gradient of angular momentum. Okay, so angular momentum is going to be just vertical lines going from the equator towards higher latitudes, because with latitude angular momentum is going to increase till we reach the instability that we talked about before, because the u bar, which will have cosine phi in the denominator as you remember from before, will keep getting stronger and stronger, and that's going to break down and give us the baroclinic instabilities of the mid-latitude. Before going to that, we just set this to be 0 for steady state, and writing v tilde, the vector, as vj plus wk, where we have meridional vertical plane circulation because we have assumed zonal symmetry and latitudinal gradients are 0, so only the basic state exists. So look at the schematic diagram then. Going from the equator towards the north, you have these vertical constant angular momentum lines, and angular momentum increases towards higher latitudes. So then you have, in the case of no heating, you simply have gradient of ma being perpendicular to this, and these are the lines of gradient p being 0. Okay, this is in the case of no heat source. If we add a heat source, obviously it begins to create vertical motion and begins to distort the constant pressure surfaces, and that's going to tilt the constant angular momentum lines, and then it's going to tilt the gradient of momentum as well. At the surface you set u equal to 0, but as you go above from the equator towards the north, you have convergent flow, so you have thermal wind on this side having negative uz, whereas on the northern side of the heating you're going to have the regular temperature gradient and the vertical shear increasing with latitude. So essentially we're going to get an easterly jet on this side and westerly jet on this side. And the main thing to look for here is to see how strong the heating has to be. Okay, if you do the simple calculations we will do in a minute, as you will see, the pressure lines will continue to be lifted, and the angular momentum lines will continue to be distorted till the gradient of the MA is pointing straight down towards Earth. In other words, the angular momentum lines essentially, instead of being perpendicular to the surface, they are going to become almost parallel to the surface. That's the condition when you are going to set up this meridional circulation that we are seeking. So think about that in terms of just the physics, then it's easier. At least heuristically, with this simple argument, steady state zonally symmetric flow, we can argue that the heat source has to be so strong that it's going to lift the surface and distort the angular momentum lines and create angular momentum parallel to the ground surface and create angular momentum gradient towards the ground, and then give us this thermally direct circulation with rising air towards the heating divergence and then sinking ahead of it towards the equator. This scale obviously is determined by how strong this heating is. In terms of equations, maybe I should leave this here and come back in the next podcast because this is already 15 minutes, but we'll just look at few equations and try to interpret this and look at why this is so different than West Africa and Australia.